Okay, guys, still now we see about and skid steering plugins, how to add in our robot and move the robot using a teleop keyboard node. After that, we are going to clone our new robot into our repository from my repository to our ROS workstation. Uh, I give that repository link in description. Okay, now we have opened the terminal and go to our workspace CD simulation and SRC source folder and git clone and paste that repository link into that SRC folder. After enter that, give enter key and it will be cloned. It will take some times. After cloning, we need to make catkin workspace. Catkin make. It will be make the essential package into our workspace. After making catkin make, we are going to launch what are the files available on that repository, which is downloaded from Git source. Okay, okay. Now that rover description is our robot file. Go into that file and see what are the files available on that, and go to gazebo.launch ROS launch. We need to make on that the display.launch will be launched an Rviz visualization software, and the and gazebo.launch will launch the gazebo simulation software first. ROS launch gazebo.launch. It will launch our simulation environment in gazebo. Okay, now the gazebo environment is launched in our Ubuntu. Uh, how will we give the color coding to our robot is a main important topic in this. Now I'm opening my Visual Studio video editor. Sorry, code editor. After opening that, I'm going to my robot folder, which is in rover description underscore description. That black wheel and the lidar is in blue, camera in green. That all are given in go to URDF file. In URDF file, the rover dot gazebo. It will have an geometrical and inertia collisions properties and an uh, all the things information about the robot will we have. What are the material colors? We need to give the first of all we design a robot by basics types. Body is separate, wheel is separate, camera and lidar will be separate. Like that only the whole information will be saved in separate. So we need to give the reference name. Once you have a body color, that's a reference name of base link. So you need to give the silver is in body color body underscore color. Okay, so silver is reflected to the base. Okay, after that for base link and body color will be reflected. After that for wheel we are giving you body underscore wheel. For that we give the black color, and for lidar body underscore lidar we give the blue color, and camera body underscore camera, it's in reference name. Body underscore is in reference name of that components or no body. Okay, after we give the reference name, we give the colors to that one. Now we are going to launch an visualization software Rviz by using a ROS launch display.launch. So it will launch an Rviz visualization software. Okay, after launching the Rviz in our Gazebo environment, using Rviz we can see the sensors reading in our Rviz visualization software. First of all, what is TF? We need to know transformation coordination frame data will be reflected on Rviz. It will be it is in base of localization. So TF is in localization base, and we can see the camera lidar and that output will be reflected to our office. Okay, guys, still now see how to clone our robot from an GitHub repository to our workspace. Now we are going to add an plugins to our robot. Plugins is nothing but it will be move the robot and it will give the uh, sensors, camera, all the working model will be given by that given to the simulation by the plugins only. Uh, the plugins are all are have an Gazebo official website for an LiDAR, for an IMU, for an GPS, for camera, and differential drives, skid steering. All the plugins are available on Gazebo official website. What I do in this video means that all the uh, plugins all are already in my GitHub repository, especially for I did for this robot. That also I will give in my description in a YouTube video. Now we are going to clone this repository to our ROS workspace, which is in simulation source folder. That is our workspace name. Whatever you need, or whatever you need for that name, or you can give to that. I am going to clone that plugins to in my workspace. Get clone that link which is copy from GitHub. It will be pasted in my terminal and enter it. It will clone it in our workspace. Now I'm going to make a catkin mix, or else you go to that repository which is cloned for plugins. After clone that one, open that plugin directory, and we have three: camera, lidar, and skid steering. Three plugins available on that repository. Now I'm going to open that one skid steering repository, and I'm going to copy that whole codes to my rover.gazebo. That is file available on URDF. Okay, we need to copy and paste it to that rover.launch. This plugin is skid steering plugin, which will move the robot by using a teleop signal, pulse width modulation signal in hardware. In simulation, that CMD will listen topic, and hardware also CMD will listen topic for lower teleoperation motion or lower control things. So that CMD will listen basic topic. I'm going to copy and paste that plugin to my rover.gazebo. After that, I'm going to make a catkin make. Okay, catkin make. Totally three plugins available on that repository. First, I'm going to launch an Gazebo. ROS launch Gazebo dot launch that will launch a Gazebo environment first. Now we add an skid steering plugin to our robot. So using ROS run teleoperate twist keyboard teleoperate twist keyboard dot py, it will be run the robot by using that keyboard command. So once you press W, it will be move forward. K means stop. L means go linear. IM means it will come reverse. Like that, robot will do. Now I'm going to launch an Gazebo first. After launching Gazebo, we need to run on ROS run teleoperate twist keyboard teleoperate twist keyboard dot py. This is an node which will be run on teleoperate node or teleoperate on signals to our robot. You need to open a terminal and run that command. That command is subscript to CMDVL topic. That node will be publish the signals to PWM. CMDVL topic. So the robot will receive the signals from the keyboards. Okay, that CMDVL topic is available on using ROS topic list. What are the topics is run on our workspace will be reflected using that command. Now we are on that teleoperation. Now we need to on the robot simulation. After that, we are going to run the robot using the keyboard. Our robot is moving now. Now it's rotating. By using on U, we can move the robot in rotation and forward, reverse motion by different key commands. Okay, after that, we are going to add an camera plugins to our robot. For adding camera plugins, it will be C by RQD or an Rviz, which is an Rviz is an visualization software. Rviz also visualization software. Using both, we can see the camera output in Rviz or RQD. Now we are going to add an that plugin to our workspace in rover.gazebo. We need to copy that whole command to our workspace. Where we need to see means in sacro files, the name of the camera underscore dot camera, that name of the components will be reflected in that sacro file. We need to see that is a reference link of an robot. We need to copy that reference link and paste it in our plugins link area. So copy and paste that one, it will be work in a real camera like in simulation. Okay. After adding that, now we can see using a ROS topic list, our camera node is on running. Using a camera plugin, the topics using a ROS topic list, what are the topics running on our ROS environment will be reflected in terminal and also in QD. And we are going to add an opening always and add an ROS topic which is available on camera for. We are going to add the topic to our always, and that always will be give the camera output of the image in reflected in our always environment visualization software. Okay, after adding, we are going to see the output of that image into our always. We are going to add some object to our Gazebo environment, and it will be reflected in always environment. Okay, now we add an on object in our Gazebo, and it in using a camera plugins, it will be reflected to our always. Okay. After that, adding camera plugins, we are going to add an lidar plugin. Is one of the essential part in robotics, and using lidar plugins, we are going to make an camera of an map of an environment using that scan lidar. That lidar have a topic of scan. Now we are going to copy the whole lidar plugin into our uh, rover.gazebo and paste it to whole whole plugins into our gazebo.launch. That also I'm already give that reference link in that GitHub repository. What we need to do means we need to do the reverse engineering using that repository, so we can understand what are the things available on that plugins and in my robot. Okay, and I'm going to copy whole things from that links and and paste it in my rover.gazebo. After pasting that, we are going to I am going to we are going to launch a gazebo. After pasting ladder plugin to our workspace, we are going to launch an gazebo environment. Now we see the scanned output in gazebo environment. After seeing scanned output, we are adding some object to that, so only we can see that scan data are reflected to our RV's environment. We are going to launch an Rviz using a ROS launch or display.launch. It will be run the Rviz now, and go to add and go to Rviz and go to add a topics which is available. It's a scan is unavailable to topics, my topics, and add and scan and raw image compression. It will be give the image data to our workspace. After that, we are going to launch an ROS run teleop to sticky keyboard is an teleoperation node. After that, we are going to launch an IQD graph vision visualize one of the visualization software. After launching RQD, using RQD, we can see what are the topics run, what are my nodes run, topics run, and we can make an teleoperation using a virtual joystick, and we can see the image by using an RQD graph. What are the using that topic? See, we have the image, and we have the TF tree. TF is nothing but transformation coordination. Transformation is a reference link. How you take the example of human body, uh, joints links where it's located in our body. We know the hands, and the hands is the best example of our TF for human body. Once our hand is broken, we can find out where is our hand. It will be get out of our body. So TF is one of the main part in robotics. So without TF, we can't make the G mapping. Okay, TF is nothing but it's an odometry data, but in odometry is an sensor feedback on a sensor data, and using that sensor data only the TF also take over. Okay, now we are making a teleoperation using virtual joystick mode. After that, we are going to delete all the object which are in Gazebo, and we are going to add an one virtual home setup in Gazebo, which is already inbuilt in Gazebo environment. Okay, now we are adding the home setup into our robot. After that, we are going to launch an visualization software office, and it will be reflected on scan data, and the object will be in red color. That is in lidar data, and camera data also will reflect in office. After that, after this, we are going to make an mapping process. We are going to use a two mapping process, which is in G mapping and hectare mapping. First, I'm going to make a G mapping. After that, I'm going to make a hectare mapping. After making mapping, I'm going to save the map using a map server. That will be save the two types of file, .yaml and a pgm file format. After that, we are going to enter into that navigation stack using a amcl algorithm, adaptive monte carlo localization algorithm, and move based algorithm. Both all are I have already uploaded in my git repository. That also will be given in a description of a video. You can take and do your own for an G mapping and hectare mapping. Also, I am already created a, repository in my GitHub. That will be also given in description. Okay, thank you. We will see in next video, which is making a mapping of an this virtual home. Okay, thank you.